Hi, we are the team, or Team 14. We are Paula Espinosa,
Jennifer Burke,
Caitlin Crawford.
Lee,
and Zach Mesker.
and today we're presenting our final ChE 470 presentation, sponsored by Lion Chemical. So in this presentation, we will talk about a project description, our main product, Cumene, the process overview of our plant, the economics behind it, and our conclusions and recommendations. So starting with project description, the Lion Chemical plant is located on the Gulf Coast in Houston, Texas, on an existing plant site. The Lion Research and Development team has been working on a new zeolite catalyst that increases the selectivity to cumene to produce cumene from propylene and benzene. Our main goal is to determine the potential value of a cumene producing plant built on this existing plant. So the plant is expected to be installed this year, 2020. It'll take around 3 years, and with expected startup date of 2023, the year 2023, and a total project life of 18 years with 15 years of actual operation, 50 weeks per year. So this cumene plant was designed to operate at a capacity of 380 million pounds per year at a high purity of cumene of 99.9%. To produce our main product in this plant, we use two different reactions. The first one is alkylation reaction, which is a reaction between propylene and benzene with the catalyst to produce cumene. This reaction produces several byproducts, and one of them is DIPB, which is used in the transalkylation reaction with benzene to produce cumene. So now let's talk about our product cumene. So we were able to meet the hard specifications for the product for sale. We achieved the final product flow rate or capacity of 45,238 pounds per hour. Our cumene ended up being 99.99% pure, with very small impurities from DIPB, ethylbenzene, butylbenzene, and toluene. For the reactors, we also had to meet some specifications in terms of the feed and the reactor conditions. So we were able to stay at a safe temperature and pressure in both of our alkylation and transalkylation reactors, and we met with all the maximum concentrations of components to limit the amount of byproduct production. However, we did not meet all the specifications required for selectivity and conversion of our components, but that differed slightly from the R&D data, but that didn't make a significant change in our process. So our plant did not meet all the sub-specifications, also due to recycle issues that we had when implementing recycle streams in our process. And so we only had a 30% and 54% benzene and propylene utilization, respectively, and 53% of our fresh benzene went to waste. And then for the IPB, we were only able to recover 2.8%, and for cumene, only 73%.
So now that we talked about our product cumene, we could talk a little bit about how the process makes the cumene. And with that comes a step-by-step, pretty much procedural look at how our process is able to do that. So it starts out with a feed purification step with a subsequent alkylation reaction to produce impure cumene and some other side products. So as I mentioned, that's step one, where we have our benzene feed go through a single separator and have our purified benzene come out of the distillate while our toluene waste stream comes out of the bottoms. In step two, that purified benzene comes together with a propylene feed ushered in from a nearby pipeline, where it reacts in our alkylation reactor at a 2.3 to 1 ratio of benzene to propylene, where it synthesizes the cumene, DIPB, and other side products in an impure form. So the cumene that was produced passes through a series of separations which output pure cumene and a DIPB purified stream. So that's seen in step 3 and 4, where you have the outlet of the alkylation reactor move through multiple separators, starting with a benzene separator, then cumene and DIPB, outputting a purified cumene and purified DIPB stream. Step 4 is to take the purified DIPB stream, combine it with a unpurified benzene feed, where it can then be combined in the transalkylation reactor in a ratio of 6:1 benzene to DIPB, where it then again creates a cumene, residual DIPB, and side product stream. The last step of our process is to purify the stream that was just formed in the transalkylation reactor. So the cumene product passes through another series of separations, which output more pure cumene. And this purified cumene stream is then combined with the stream that was made in step 3, and from there on out, it is sold for product. So that concludes our process overview, and we can move on to the economics of the project.
Okay, so to begin our economic analysis, the first thing we looked at was the total capital estimate for the cost of our cumene production plant. So we started by looking at the overall capital, so that includes the IBL, process equipment, the existing OBL that needed some upgrades, and then all the miscellaneous costs that you see on the left side of this pie chart. So the IBL and the OBL make up the total contractor cost, and from that total, 8% of that total was added for team costs, 4% of that total was added for miscellaneous costs, and 7% of that total was added for pre-operation and startup costs. All of those summed together equal the current point estimate, and from the current point estimate, 13% was added for escalation and 20% was added for project contingency. As you can see, of the total capital, $51.1 million goes to the IBL, which is about 44% of our total capital estimate. So looking deeper into the IBL, all of our pieces of equipment were put into Icarus to price them based off of their sizing characteristics. So this table shows what was entered for each different type of equipment into Icarus to get its price. So each different piece of equipment had different characteristics, such as columns were the length and the diameter, heat exchangers had area, and so on. All of them had a design pressure, temperature, and material of construction entered into Icarus. For our columns, we were able to save some money with some of the columns having a smaller top diameter than the bottom diameter. All of the material for each piece of equipment was A515 or carbon steel, except for the trays of the columns, which was SS140 as an input in Icarus. All of our pumps in the process are centrifugal, all of our reboilers are thermosiphons, and our heat exchangers are U-tube heat exchangers. For the reactor, Icarus does not have a PFR input, so we had to input the reactor as a packed bed tower. So that had similar inputs as a regular column. Then just a detailed summary of the cost of the IBL. There were a couple key pieces of equipment here. One we'll start with is the toluene tower, making up $10.4 million of the $51 million IBL cost. So as you can see here, there are a lot of pieces of equipment that go into the toluene separator unit operation, which is one reason why it is so expensive in comparison to other unit operations. For instance, there are 6 heat exchangers, 4 pumps, 3 drums, so a lot of equipment that was required for this section of the plant. It's also seen, as you can see on the right there in that bar graph, that some of the characteristics of each of our pieces of equipment in this unit operation had higher values than the overall average for the plant. So the heat exchanger area was very high, the pump flow and the volume of tanks is also very high. This is due to the fact that it is the first unit operation in our process, so it is seeing those high flows from the OBL of our benzene feed. All right, another key piece of equipment is our benzene separator 2. So this piece of equipment, for very similar reasons, is expensive because of such high flow rates, and that is seen through the heat exchanger area primarily. So as you can see on the right, the heat exchanger area average for the heat exchangers in this process, or in this unit operation, are much higher than the average for the overall plant. It's a comparison of about 15,000 to about 2,000. There aren't an overabundance of pieces of equipment in this unit operation. It's purely just the sizing of each piece of equipment. Okay, and then to look at our OBL a little bit, the OBL cost is 50% comprised of just the raw material cost. And this is due, raw material, product, and product storage. This is due to high flow rates of raw material needed for our process. And then all of the things in the OBL needed to be upgraded from the pre-existing site, but the site development and raw material and product storage can be seen, their cost was calculated from that equation on the bottom. So that's based off the capacity term mostly. So since our capacity for our process is higher than the capacity that it was already built for, there's going to be an increase in the cost than it was for the previous capacity. But all things are also determined based off of time and location factors. So locations around the United States have different factors that are added into the cost, as well as the time from the past production to our future production with our new plant.
So in order to determine the quality and the efficiency of our base case process, which was previously described, 2 alternative studies were performed. Each study was analyzed based on overall impact to the process quality and its viability. So the first study includes adding a second column to the benzene feed purification system. And the intention for this is to remove as much toluene from the benzene, which would allow a saleable toluene. It is determined that the overall cost of this modification would be approximately $435,000, and the hourly profit would be around $886. The payoff for this equipment addition would only take 21 days. This modification was therefore determined to be beneficial to the system, and it would be recommended that this piece of equipment be added after the startup, given that there is space for this equipment. The second study is focused more around reducing costs. So in the study, we removed the transalkylation reactor and its supporting equipment. It was analyzed and determined that this would save around $14 million. However, it would probably not be viable due to the fact that the amount of DIPB produced would be higher than the ppm allowance in the waste stream without the reactor. So unless there is a catalyst or process that suppresses the production of DIPB found, this modification we determined was not valid.
So the cash flow model shows a negative overall return from the start of the plant's lifetime for the entire 18 years, mainly due to the raw material cost. And the cash flow model looks at the overall, essentially cash flow for the entire plant. It starts off by looking at the capital that Kate talked about earlier, and then it also expands into 4 additional categories. So the first category looks at the raw material costs that I mentioned earlier, and that includes the propylene and benzene feeds, as well as the 2 different catalyst particles, one for the alkylation reactor and the second for the transalkylation reactor. The second part of the cash flow that's new is the byproduct costs. And in our plant specific case, they're less of a cost and more of a benefit, because we are actually producing steam by evaporating DI water in our reactor cooling system. And we're also burning our vapor waste and liquid waste, because the heats of combustion are actually comparable to that of natural gas. So we can sell it for a fuel credit at 60% of the natural gas price. Thirdly, we have utility costs. And as Kate mentioned with the OBL, there are specific utilities that we use, such as cooling water, all the different variations of steam, as well as power in order to operate our pumps and compressors. And lastly, we have fixed costs, which include repairs and maintenance. It includes labor, property tax, insurance, and overhead. So to give you a perspective on how much of a dominance that the raw material cost has on the plant, I changed the areas of the specific categories to model it based on their total impact on the process. And as you can see by this slide, the raw material has a 91% dominance on the total cash flow model for these 4 categories specifically, excluding capital. And showing that in another way, you can see this in terms of a pie graph where the raw materials take up the vast majority of the graph, with the total byproducts being represented by a negative number. But this was only done to get a full 100% category by adding up the absolute values rather than the values seen here. And the current state of this process actually does not allow for a reasonable calculation of a net present worth after tax rate of return, or IRR. We were able to calculate a net present worth at negative $713 million at the end of our process's life, and this is with a consistent cumene price of 42 cents per pound for the product cumene. However, what we were able to do was determine a product price to achieve an ATROR of 15%. And that product price needs to increase by 104% to 85.7 cents per pound for our product cumene. And this ATROR was found by solving for when it equals 0 for our constant discount rate.
So as Zach said, this project currently is not profitable. So 4 sensitivities were performed in order to analyze specific conditions that could potentially make this project profitable. The first study was performed, and it was an analysis of the natural gas prices. As you can see from the diagram below, our base case used a natural gas price around $1.56 or around $1.88. It fluctuates. This value is the lowest natural gas price seen in the past 10 years, and this can be attributed to the current state of the economy due to COVID-19. To create a more accurate representation of utility cost, a moderate or average natural gas price was used and a high natural gas price was used. As you can see, the moderate price is approximately $2.62, and the high price is approximately $4.37. Due to the fact that utility costs are approximately 3% of the total project cost, these fluctuations in natural gas price had nearly no effect on the overall costs. Therefore, a high, low, or moderate natural gas price would not be significant enough to make this project profitable. Additionally, a sensitivity was run on the project's raw materials. As you can see from the chart, the raw materials costs have the greatest impact on the overall project costs. So raw material, which is shown in the blue, it takes up around 91% of the entire project cost. Because of this, a sensitivity was run for when these raw material unit prices could increase or decrease by 10%. It was then compared to the base case. When the raw material unit prices are decreased by 10%, the project costs decrease by approximately $8 million per year. It is therefore recommended that any changes that would be researched and executed would be made in regard to the raw material costs. However, even with this decrease of 10% in raw material costs, the project still remained unprofitable.
Well, for the fixed cost sensitivity analysis, there are 4 kinds of costs in the fixed cost. There are the labor cost, property tax, repair and maintenance cost, and insurance cost. Among them, the property tax, repair and maintenance cost, and insurance cost are at the specific ratio of the capital cost. However, for the labor cost, there are 2 elements. They are the unit labor cost and the number of the laborers. The number of the laborers is decided by the equipment requirements. So when the capital cost is fixed, the only thing that will change the fixed cost is the unit labor cost. So we did some research on the unit labor cost from the data that provided by the National Labor Status. We found that the unit labor cost will change over time, accompanied by continued growth in some fluctuations. Furthermore, after we analyze the relationship between the total cash cost and the unit labor cost and time, we found that the total cash cost will increase with the unit labor cost and time. Because our project is not profitable at the current raw material cost and utility cost, we analyze the expected Cumene selling price when we achieve the design goal of after-tax rate of return equals 15%. We find that we just need to increase the expected Cumene price by 0.0004 cents per pound to face a 3.5 annual increase in unit labor cost. About 3 sensitivity studies are all about the cost. However, the final sensitivity study is about the product value of the Cumene. From the previous introduction, we know that only when the price of Cumene reaches 85.7 cents per pound can we achieve the design goal of the after-tax rate of return equals 15. So we did some research that the range of the price of Cumene is between 42 to 81.6 cents per pound, which means at current conditions, our project will never be profitable and achieve the design goal of the after-tax rate of return equals 15%. And the things above is the economies. And the next thing that I'm going to talk about is the recommendations. In conclusion, this group does not recommend that the construction phase is started for the project. Although the process is well defined, our economy analysis indicates that the project should not be executed. As you can see, all 4 sensitivities were performed to evaluate if this project could ever be profitable, and all scenarios shows that it could not be given this capacity of Cumene production. We thank you for your time and attention throughout our presentation. Thank you.